Hello everyone, in this video we'll be solving problem 139 word break. The problem statement is we are given a string S and a dictionary of strings word dictionary. We need to return true if S can be segmented into space separated sequence of one or more dictionary words. In simple terms, we need to return true if the words created from string S by placing separators at the right position exist in the word dictionary. For instance, in example number 1, where string S contains LeetCode, if we place the separator right between T and C, the two words that will be created are leet and code. Both of the words exist in the dictionary, hence we return true. Similarly, in example number 2, we can place two separators in the string S, which will give us two instances of apple and one instance of pen. Both of the words exist in the dictionary, hence the output is true. I trust you were able to understand the problem statement. Now let's switch to whiteboard and discuss how we can solve this problem efficiently. Like every other problem, this problem can also be solved using brute force approach, where we'll run multiple iterations to check if the words in the dictionary exist in the string S. If it does, then we'll replace it with empty string. The expectation is that after we completed the loop, the string S should be empty. Let's do a quick dry run starting with the first element in the dictionary, that is cats. As the word exists, we'll replace it with empty characters or basically remove it. Next word is dog. As it exists in the string, we'll replace it with an empty string and continue with the remaining characters. Now we are left with an. As an does not exist in the dictionary, our output should be false. But this output is incorrect. We have only tried the combination starting with the first element in the dictionary to check if it exists in string. It is always possible that we can place the separator at a different position which can yield us a different results. For example, if we would have started the check with cat as the first element, which is at index 4, we could have gotten a different results. We would have eliminated cat first, after that SAN would be the next word, and because we need to compare all of the words, we'll reset the pointer to start from the beginning when we are at the end and continue with the comparison. And when our pointer is pointing at the word dog, we'll find it in the remaining characters in string S, so we'll replace it with empty string, and at the end we'll be left with no characters. Hence the output will be true. Basically, we need to run the iteration with all of the words as the starting point in the dictionary to make sure we are covering all of the combinations before returning the results. With this solution, our time complexity is O of 2 raised to power n, where n is the size of the input string. This is because of the comparison that we are doing between the words in the dictionary and the characters in string S. While the space complexity is O of 1, as we are not using any collection to maintain the record. Now let's discuss an optimized solution to solve the very same problem. One issue in the previous approach is that we had to run multiple iterations on the input dictionary to check if the word exists in the string S. Due to that, there were several duplicate calculations that had to be done, which was increasing our overall time complexity. For example, in one of the iterations, we would have identified that the word cat exists in the dictionary. So we would place a separator right over there between T and S. But there's one more word cats with plural S which also exists. Now if we want to process CATS, we would have repeated the calculation of comparison for CAT again. Now if we can think of an approach that can help us avoid these duplicate calculations, the solution will be much faster. This is the best use case where we can use dynamic programming array that will suggest if the word exists in the dictionary that ends at the corresponding index in the original input string. Let's run a couple of simulations to understand how dynamic programming can help. As there are a total of 9 characters in the string, we'll use the dynamic programming array of length n plus 1, that is 10. The first element in the array will suggest the value for an empty string, that is no characters in input S. And if the string is empty, it by default exists in the word dictionary, So the default value in DP of 0 will be true. As discussed earlier, this dynamic programming array will help us record the value if we can create or segment the string from 0 to the particular index where all of the words created after segmenting exist in the dictionary. Let's start with the first character C. Does it exist in the dictionary? No, it does not. So we'll set false and move on to the next character, which is A. As the character A by itself do not exist in the dictionary, we need to try to combine it with all of the characters before it to see if the combination exists. Now we'll try. As the character before A is C, we'll check if CA exists. No, there is no such word in the dictionary. So we'll say false in the DP array. Moving on to the next element, which is T. T does not exist by itself in the dictionary. Now we'll try to combine it with the one character before, which is AT. Does AT exist in the dictionary? No, it does not. So we'll extend the range to include C as well. So the word is cat, which exists in the dictionary. So we'll place true in the DP array for that position. Moving on to the next character, which is S. S does not exist by itself in the input dictionary. So we'll try to include more characters. So TS, does it exist? No, it does not. ATS doesn't exist either. CATS, yes, that word exists. So I'll save true to the array and increment the pointer. Next character is A. A does not exist, so we'll include S. SA doesn't exist either. TSA doesn't exist. All of the characters that if we include do not exist in the input dictionary. So we'll save false at that position. Next character is N. N does not exist in the dictionary. So we'll include A to it. AN doesn't exist either. So we'll include S. The word exists after including S to it. Here's where things get interesting. We cannot simply put true here because we want to make sure that if we are taking SAN as one of the words before it should also exist in the dictionary. As we are trying to build the solution on top of the previously calculated combinations, we should make sure that all of the words before SAN is also valid and exists in the dictionary. If the previous word does not exist, it doesn't matter if SAN exists in the dictionary. Our final output will still be false. Along with checking the value SAN exists in the dictionary, we also need to use the dynamic programming array to check all of the words right before it if the corresponding value is true. In this case, the value is true, so we can place true for the position n in the DP array. Moving on to the next character, which is D. D does not exist. The combination of N and D also doesn't exist, but A and D does. Similar to the previous approach, we'll look up the character right before A if its corresponding value in DP is true. As the value for S as the last character is true in the DP array, I can place true for D as well. Moving on to the next character, which is O. O doesn't exist. DO doesn't exist either. There are no words in the entire dictionary that ends with O, so we can safely put false at this position. The last character is G. G doesn't exist. OG doesn't exist either, but DOG does. So we'll just verify the character before that, what is the corresponding value in the DP array. As the value is true, we can place true for G as well. Once the iteration is complete, we'll return the value saved at the last element in the dynamic programming array as our output. With this solution, our time complexity is improved to O of n square, where n is the size of the input array. The reason it is n square is because we are running two nested iterations, one to identify the last character and then going towards the left hand side to see if we can build the combination of words that exist in the dictionary. And the space complexity is O of n, as we are using this dynamic programming array to record the values at each position to check if it can be segmented. I hope you were able to understand the explanation. Let me show you how we can implement this approach using C#. In this C# implementation, I am validating both word dictionary and S are not null. If either of them are, I am returning false. After that, I'm converting the list of string, that is dictionary, into a hash set for faster lookups. On the next line, I'm initializing a DP array of type boolean, setting the length to n plus 1. And as we discussed, the first element in the array will always be true as it represents empty string. After that, I'm starting a for loop with I is equals to 1. This pointer will be pointing at the character which is going to be the last character in the word. Inside it, I'm starting another for loop to iterate through all of the elements from 0 all the way to I. I'm using this pointer j to determine the starting index of the word. Inside the for loop, I'm checking if the word that is built using the positions of j and I, if it exists in the dictionary, and the value at j, which is the previous value in the DP array, is it true. If both of the conditions are met, then we'll set DP of I to true and jump out of the inner for loop. After the outer for loop is complete, I am returning the value in the DP array at n position as the output. This code, when submitted on LeetCode, beats 52% of the submissions in terms of runtime and 21% in terms of memory. Thank you for watching this video. I hope you were able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.